Okay, so it's a great pleasure to have a I²CNER seminar. This is the first seminar at the beginning of this new semester. And today we have a speaker from CNRS, France. And at present, Dr. Bruno Ameduri. And at present, he is visiting professor of the Institute of Materials Chemistry and Engineering, Kyushu University. And he's going to stay 1 month in our group. Just above this building. So let me introduce briefly about Dr. Ameduri. And he got a degree of chemical engineering and a bachelor degree from ENS Chimie, Montpellier, in France. So Montpellier is a city located in the south part of France. And then he got a master degree, Master of Science from University of Laval in Quebec in 1986 under the supervision of the Professor Prudhomme. He's also one of the very famous person in polymer brands. And also, after that, he got PhD from University of Montpellier, Dr. Boteven, and he is very famous in the fluorine chemistry. And he has experience as a postdoc in IBM San Jose in 1986. So his research was Langmuir project film. So it's a completely different topic from the present today's talk. And also he has experience of at the I²CNER research on chlorinated paint. So he has a very he's a very active person, and he visited several times to Kyushu University. And also one of the very important activity of his research is today's topic is closely related to is a fluorinated polymer, especially from the synthesis to the applications. So he has published several books and also more than 200 publications, and he has 60 patents. And I guess he just recently got awards from French government, right, Bruno? Yeah. So, and also he is very active as a editorial board of Journal of Fluorine Chemistry and the European Polymer Journal and the Polymer Bulletin, and also Polymer Journal on Japan. And in this case, he's an associate editor. So today, he has several topics, but at this occasion, we are going to have the I²CNER seminar. So we choose the right topic for the audience. The title of his talk is Recent Advances on Fluoromembrane for fuel cell. So let's welcome Dr. Bruno Ameduri.
ありがとうございます。Takahara Sensei, it's my real pleasure here to be in Kyushu again. This is my third time, and I always enjoy coming to Japan. It's also my pleasure and I would like to thank you very much for your kind invitation here. 1 month is a beautiful time, and this is also Sakura, cherry blossom here, but I really appreciate. Also, I'm very impressed by this fuel cell division and this International Center for Carbon Energy Research. And I'm sure that everybody here is very proud of these facilities. And I see that in a couple of months, you will have even a bigger building so that you will be very competitive in energy. So I'm very happy to be here. And as Takahara-sensei mentioned, I will give a couple of seminars related to fluoropolymers because this is my topic. Today I'm going to talk about some work we have been developing in the lab regarding some fluorinated materials for fuel cell membrane. I know among you, many people are working on fuel cell, so I can be a little bit redundant, and a lot of preliminary notions will be already known because most of you know this information. But where do I come from? Just let me introduce my city. This is Western Europe. Here, this is France. Maybe some of you have been to Paris. But there is not only Paris in France, and if you have a chance to go to province, you can go to the south, where my city is in Montpellier. Very interestingly, we have the sea, Chichukai, Mediterranean Sea here, and it's a little bit far, it's 10 miles, but it's a very nice place to visit, and please let me know if you have a chance. Takahara-sensei came several times, and I think he will come again. This city is involved in a winery place. Of course, it's not as prestigious as Bordeaux. Bordeaux is here, and Burgundy is here, but we have a couple of wines. And also we have a patchwork of architectures. This is the new Place de la Comédie, the square, which is the main square. We have medieval style. We have here the Faculty of Medicine, which is one of the oldest Faculty of Medicine in Europe, which is close to the cathedral. You see the baldachin entrance, which is very unique here. This kind of different architectures made us thinking that probably we can do also some designing of architectures on polymers, and especially in fluoropolymers. If you don't mind, I would like to remind you that fluoropolymers are niche macromolecules, but very unique because they have remarkable properties for specific applications. For instance, they have low refractive index for optical fibers. They have low surface energy for lubricant, for release. They have high all-water soil repellency for many protections of substrate, just like textile, leather, paper, concrete, glass, stone. We had a lot of program with corrosion of old buildings in Europe, and fluorinated polymers have been very useful, just like here in Paris. This is the Arch of La Défense coated with PVDF. Fluorinated polymers are highly chemically, thermally, oxidatively stable. And these requirements are very important for fuel cell. We will see that a little bit later on. For not only for protective coatings, but also for fuel cell. This is a stack of different units of membrane electrode assembly. I will come back a little bit later on. But you have to be sure that this material can withstand very high acidity or very low acidity, and also they are oxidative resistant. Because when a fuel cell is working, it generates a lot of water. The water is oxidized, generating hydrogen peroxide, and the radicals are really attacking the polymers, so that hydrogenated polymers cannot fulfill the game for having a nice material for membranes. Fluorinated polymers have low surface tension. They can be used as surfactants and firefighting agents. I will have a chance to give a talk to PhD students, and of course you are welcome on this topic. Surfactants have big problem issues because they are bioaccumulable. So I regret to tell you that most of you have some fluorine in the blood, and the half-life of fluorinated surfactants is about 3 to 5 years. Maybe I have a little bit more because I'm every day in contact with fluorinated material. Fluorinated material polymers are also electrically stable. They can be used in lithium-ion batteries and proton exchange membrane. Of course, this is the topic of today. And also they have been used in insulation for cable and wiring industry. So you can see that remarkable application, remarkable properties for key high-tech applications. What we are doing in the lab just briefly, is we work a lot on fluorinated telomers, low molecular weight polymers, that I will talk about in a couple of days in Kyushu, and also on copolymers. Usually the fluorinated alkenes, just like TFE, vanillin fluoride, trifluoroethylene, or others, are gas. And you have to run to carry out your reaction in autoclaves. So sometimes you reach very high pressure. But what is interesting, when you see the drop of pressure, this means that your monomer, the alkene, the gas, is going to be consumed and to be incorporated in the homopolymer or copolymer. And this is sometimes what you obtain after. This is not. This is very interesting because you see a lot of crystallinity of your system. So we have several topics. We do a lot of work on basic research in kinetics, for instance, but also we study the synthesis, the characterization, let's say the spectroscopic characterization, and the mechanical thermal properties. And we do applications, of course, like in fuel cell membranes. So these are a batch of different pictures. I will come back on that. We work on surfactant in order to try to find out biodegradable bonds for surfactants. And these are some surface tension versus the concentration of surfactant. We work also on fluoroelastomers, and we have been very lucky because we have been working in collaboration with DuPont in the US in order to try to find out new elastomers. And also, least but not last, we are working lithium-ion batteries and nanocomposites. And this second topic will be also disclosed in a presentation. So it's a brief overview of what we are doing. This is a very short summarize, but today I would like to concentrate on fuel cell membrane. And fuel cell membrane, why is it so more important? Because you can have a new energy in a clean energy. You know, now the system of energy is a problem with oil recession, with gas recession. You have a lot of fossil sources, coal, oil, gas, uranium. So geothermal, you have a lot of activity in Japan, hydrothermal system, but also you have renewable resources of energy, just like wind, sun. Sun is for 5 billion years. So if you can find some photovoltaic, I was surprised that in this international center there was not much work on fuel cell, on photovoltaic applications and biomass. And if you want to generate some clean vector of energy, just like hydrogen, it's difficult to produce hydrogen. You know that. I just visited the nice stuff to produce the hydrogen from electrolysis of water. But usually the water unable to give you hydrogen, which is difficult to find in the mother nature. And from this fuel, it's possible to direct and to have some applications, just like transportation, stationary, or other systems to generate electricity. So this is very, very important to find a fuel and also material which are appropriate for fuel cell. So now, according to the power which is generated from fuel cell, you can have different applications. You can have even biofuel cells, or portable systems, or even for transportation, and for higher energy generated, you can have bigger transportation and also stationary. And obviously, most of you know that it's not possible to have one unique membrane which is able to fulfill all these applications. And of course, you have to find out the most appropriate system in order to generate the power you are looking for. So these are also some applications. You can see the technology is very difficult and complex. You have a reserve of hydrogen in this case, and all the stuff, the chemical engineering and process engineering in this engine. So this means indeed that you have really to find out solutions, how to produce and how to store the fuel. And of course, you need a lot of help, some engineers, in order to assist you for running your membrane. So this is a Stark, which is about 50 MEA. I will come back on membrane electrode assembly. When you have a membrane, you need catalyst, and then you have to make the first elementary element. And when this works, then you have to do that maybe 50 times to have a stack. So just an information here, these are some cameras which are fueled with methanol. So it can be very interesting, the technology, because methanol, it's a little bit dangerous, but it's a liquid, so you don't have to store in high pressure system. but methanol also for what is called direct methanol fuel cell. So the money put in this research is extremely high. And what I would like to do on this map to show you that, let's say, the public funding and industrial funding from UK, from the States, the Department of Energy, Department of Transportation, Department of Defense have put a lot of money and still made a lot of money to support labs in industry. In Japan, 20-year program by NEDO, probably another system. And I'm proud that here there is, I think, a lot of money which can be put for fuel cell. Also in Canada, in Europe, I was lucky to be involved in a European program a couple of years ago, and fortunately we have 2 PhD students funded by this program. In France, we put a few amount of money. I will come back to different national programs we have been involved on. In Germany, they took also the decision to put a lot of money in the program. In Korea, in China, in India. And so you can see that there is most countries has decided to put a lot of money in this area. So now, and this is also some preliminary notions that you know all, you have different types of membrane. And I have mentioned that you cannot find a unique universal membrane for all the applications. So what you have on the left part of this figure is the temperature of use of a membrane. So this means that you can use in solid oxide fuel cell in which the electrolyte is oxide, okay, running at this high temperature, but now there is a big tendency to try to find out lower temperature. And when I was visiting the NICE center, I saw that you are trying to work at temperature lower than 700, which is a good challenge. Molten carbonate fuel cell, we have carbonate as electrolyte, phosphoric acid with, of course, I will come back here, we have tried to find out how to branch some phosphoric acid on a polymer. And you see that we are lowering the temperature in these conditions. Polymer electrolyte fuel cell membrane in which we try to have some sulfonic acid group which are able to transfer the protons. And then alkaline fuel cell in which you need another source of fuel, of electrolyte, which is usually potassium hydroxide or sodium hydroxide. But in this condition, you can understand that the fuel cell, the membrane, which is in a sandwich between both electrodes, has to withstand these conditions of electrolytes. So indeed, a lot of work has been done. And if you look at the literature, you can see that the number of publications is increasing a lot. And there was a big development from the beginning of the third millennium, starting with about 250 papers, and now you can see that it's almost 2,500. So just to keep in mind that a lot of interest have been drawn in order to find out really some material, some catalyst, some MEA, some stack, some quantum chemistry also, some calculation, in order to find out which can be the most appropriate system. So a fuel cell indeed is a converter of energy which is going to change the energy of a chemical oxidation reduction into electricity, water, and heat. And indeed the fuel, I take the example of hydrogen, is going to be generated at the anode in which you have an oxidation reaction. Leading protons, the protons are crossing the membrane and generating electrons which are able to generate a system. And then this electron can be recovered at the cathode with the protons and with air in order to generate water. So you do not produce in these conditions, you do not produce any CO2. So this is regarded as a clean process and can be very challenging. Requirements of the membranes are numerous. And believe me, it's not easy to find out the material which fulfills really all these properties. The first important requirement is the high protonic conductivity. This is very important because if you have a fantastic polymer that you cannot make in a good membrane and that cannot conduct the protons, in this case the protons, or the anions, OH minus in the case of alkaline fuel cell, you can forget. So mechanical strength, of course, membrane are electronic insulator, good gas barrier, which is very important because you don't have to mix oxygen and hydrogen. Chemical and thermal stability, electrode compatibility also very important. Okay, if you found a material which can adhere on the catalyst, this could be a very good solution. If you work in collaboration with industry, they would like you to work on cheap materials. I know that fluorinated polymers are not cheap, and also to control the water absorption and desorption. And this also has to be done in a wide range of temperature. I will go back in my presentation of this temperature, which is very important, whatever the use of different systems. And regarding the material, I'm going to focus today on the polymers and also on the membranes you are producing from these polymers. You can see that the conductivity is very important versus the temperature. So I put the temperature here on the top. For polymer electrolyte membranes, I will come back to Nafion or Flamion and sulfonated PEEK, PEK. Or at medium temperature, you can have other system with phosphoric acid, which is very interesting. Phosphoric acid, Phosphorus is very important because you can have some compatibility with electrodes. You can have flame retardancy, and you can have anti-corrosion, and you can have acidity. And I will come back also during my presentation on making some new phosphoric acid polymers. And then if you go to try to find out new solutions at high temperature, you need ceramics, just like a special pair of kit or system for low temperature solid oxide fuel cell. So of course today I will not talk about that. This is an old figure from Krüger in Germany. But what I would like to show you, these are some different pictures of different membranes. This is from a friend of mine, Régis Mercier in Lyon, working on sulfonated polyimides. This is another friend of mine, Patrick Janasch, in Lund in Sweden. He makes a lot of polysulfone. These are some Nafion membrane, you know, it's transparent. Okay, and this is one of our production, let's say, from a blend between sulfonic PEEK and fluorinated polymer. Indeed, in order to get this fuel cell, obviously you need a lot of expertise. And the area of fuel cell is really interdisciplinary. So first of all, you have to go upstream and to look at which kind of monomer I would like to do. In order to get a polymer, of course, you need a monomer. So will it be stable in the conditions? Will it be able to polymerize? And will it bring the function, just like sulfonic acid or phosphonic acid, in order to allow the conductivity? So this means that you need a lot of expertise in organic chemistry. Or you get some friend who is in a good way to produce you monomers and a reasonable high amount of monomer. Then this monomer being achieved, you have to do some polymer and homopolymerization or copolymerization. Of course, I don't go in details about kinetics. It depends on what you use. But when you have two monomers, if you start from 80-20 in the copolymer, you don't have necessary 80-20. So you need tools in order to investigate which is the concentration and the composition of the different monomers in your polymers. So this means that you need really polymer people. And I know in Kyushu you have a lot of good PI here. Thermal purification, structural characterization, which is very important. I will not talk about that, but the design of the polymer is very important, and how the system with cluster of hydrophobic cluster in a hydrophobic matrix, how this is important. Then from a polymer you have to design the membrane. And as I told you, if you have a good membrane, if you got a good polymer, maybe you will not get a good membrane. So you have to find out the good conditions in order to process the membrane. So you need a little chemical engineering on that. You have to find out which is a good solvent, non-solvent, which is the thickness, viscosity, the evaporation. If you do some casting, if you dissolve your polymer in a solvent and then you evaporate. If you evaporate too fast, you make holes, pinholes. If you evaporate too slow, you make wicks. So this is also a know-how. And very often you understand the system when you work on the bench. And when the preparation, when the membrane is ready, you have to characterize your membrane. So you need stability, water uptake, proton conductivity, mechanical properties. So this means that you need electrochemist expertise, mechanical researchers, we can help you in this way. So just to understand that all this area on this frame already requires a lot of knowledge that maybe alone you can have, because it's difficult to know all the knowledge, but you have to be in a frame of a collaborative program. After making the membrane, and if you have satisfactory properties, you have to design the membrane electrode assembly. So this means that you have to prepare some catalyst, and it's not easy, so inorganic people can help you. Inorganic chemists who know how to blend material, how to prepare, to avoid maybe some noble materials, just like platinum, is also very challenging. But from inorganic material and polymer, organic material, how can you blend this? And this is also another challenge to succeed, to fulfill that. And after that, you have to evaluate the fuel cell VMEA and to do some degradation study. This is an MEA. This is the sandwich of the membrane between the two electrodes. So starting from a monomer, you go upstream, and then you go to an application which is downstream. It's a big, big window. Okay. So I would like today to give you some information. Of course, I cannot be exhaustive in my presentation, but to give you how we can design some polymers in order to make some membrane. So I have to focus, of course, in this presentation. And I will focus only on fluorinated material. And also, I found two interesting ways. One can be a direct copolymerization. So you can choose either aliphatic fluorinated polymer or aromatic polymers. And also, the second way strategy can be how to make a chemical modification of a fluorinated or a non-fluorinated material with specific group in order to achieve the ionic exchange capacity group. So the first example I would like to give is nathium or flamium. This is a radical copolymerization of tetrafluoroethylene. Be careful, it's a gas. It's a very dangerous gas. The power of deflagration is 3 times higher than TNT. So if you use TFE, be very, very, very careful. No oxygen. Be careful. So the copolymerization of tetrafluoroethylene with this perfluorinated ether, okay, you have a perfluorinated ether. This does not homopolymerize under conditions, radical conditions, but copolymerize with TFE. And of course, a lot of work has been done on the kinetics of copolymerization. We did some work with VDF and indium fluoride kinetics in order to copolymerize with this vinyl ether. This is a specific vinyl ether which can be produced by different companies, just like DuPont, Asahi Glass, Asahi Chemicals, or Dow Chemicals, and more recently by Solvay. So this means that you have different N. This is a ring opening polymerization of hexafluoropropylene oxide from a sultone. I don't go in details, but again, organic chemistry is important. And usually this monomer contains sulfonyl fluoride N group, which is hydrolyzed later on after making the copolymer into sulfonic acid. So the design is very interesting because you have a backbone which is perfluorinated, which confers the chemical inertness, the thermal stability, the resistance to oxidation. Just remember what you call what I mentioned as properties at the beginning of a fluorinated material. And on the backbone, on the side group, you have some sulfonic acid group, which is adjacent to a CF2 electrohydrogen group, making the acidity much higher. So the design already of this polymer is very interesting. This was prepared by DuPont, okay, in the US with an Nafion. I will come back on Nafion. Or Asahi Glass and Asahi Chemical in Japan. So you have flamium membrane. And more recently, Solvay produced some Aquivion in which you don't have a spacer here, this n equals 0, and you have a shorter spacer which makes a higher crystallinity and which brings probably better properties. And still a lot of work we have there. So other interesting work has been developed by Daryl DeMarteau in Clemson University in the east coast of the US. You see this is Nafion with a high proton acidity, and this sulfonamide makes also very high proton acidity. So just a chemical change with amino allows to prepare some interesting conductivity fuel cell membrane. And this same team This is Daryl DeMarto, and this is Steve Krieger in Clemson. They show that also they could prepare some nice monomers, comonomers, perfluorinated ether containing a phosphonic group. Okay, even they did polymer with tetrafluoroethylene. And you can see the design and the composition is very important because the phosphonic acid is going to bring the acidity. And you can work at higher temperature. And when you see this polymer 21 called by this group, you have very nice compound. And this enables to have, when you study the conductivity versus temperature, to have very nice, here, the green part is a polymer containing this phosphonic acid, showing a higher conductivity than that of Nafion. Nafion is the orange curve. So always, when you do some conductivities, try to compare with Nafion. Because sometimes, if you do your experiment here in your lab, you can have with the same membrane and same conditions, but over relative humidity and temperature, you can find different conductivities. So this is very important to be reproducible in this here. What we try to do in the lab is to mimic Nafion with vanillin fluoride. We work a lot on vanillin fluoride. I told you that TFE, tetrafluoroethylene, is explosive. So I took the responsibility not to use any TFE in the lab. And we tried in copolymerization or polymerization with hexafluoropropylene and this monomer to make some new membrane, even using chlorotrifluoroethylene or even using this kind of brominated compound, which enables to make some cross-linking by the bromine and by radicals. So we play with that, polymerization, tetrapolymerization, and even with 5 monomers in order to find out new material, either by conventional radical polymerization or by contra-radical polymerization. And this is a kind of membrane that we obtain. I will go a little bit further here, but I would like to thank my co-workers, Renaud Souzy and Laurent Sauguet, who did very good PhD. They were my first PhD students, and really it was very tough at the beginning to go in this area. Another example is a French network. I will have a couple of examples of what we are doing, but this is France again with, in this partnership, we had a different team. We have 2 work packages, one work package on the characterization, another work package on the synthesis, so characterization in synthesis, let's say the west of part and the east of part, let's say. And we try to develop in a many project a hybrid polymer membrane in order to have some composite and salt gel approach. It's very tricky because again you are going to mix some organic and inorganic materials and you have to find out good membranes. So one example was developed in atomic energy, and we tried, this group tried to make some functionalization of nanofillers, just like silica, and to put sulfonic acid group on the surface, okay, and then to blend with some PVDF or even other copolymers in order to make some membrane. This is a fume cupboard in which you make the evaporation, the casting. So you have to design to mix inorganic material and a fluorinated material, which are not very friendly, but in specific conditions, there is a patent on that, it was possible. And then to characterize the membrane by electron microscopy or confocal microscopy, and then to prepare the MEA and to, thanks to electrochemists, to investigate the polarization curve. So what you go here, you increase the current and you see what's going on for the voltage, and you try to get as parallel as possible. Of course, you have some loss arising from the electrodes here and here, and also from the resistance of a membrane. So this curve, kind of curves called polarization curves, are very important because you try not to lose some voltage and to maintain the voltage. So the approach we had in the lab was to come back also to the upstream. I told you that we did some copolymerization with VDF, with vinyl tritoxysilane, and also this vinyl ether containing sulfonyl fluoride. Obviously, we did a bunch of different polymerization in order to vary the content of VDF, the content of tritoxysilane, and the content of sulfonic fluoride or sulfonic acid, in order, of course, to have some conductivity. After making the radical depolymerization, this was acidified first in lithium carbonate to have sulfonate, and then acidified into HCl to have sulfonic acid, which instantaneously, in a sol gel process, thanks to Professor Clément Sanchez-Paris, we could achieve some membrane. You see, this is kind of dense membrane, as you have here, with this is 50 micron, but more or less they are very dense, but very interesting because you blend really some fluorinated polymers here, made of PVDF and these sulfonic fluoride compounds, okay? And thanks to the trioxysilane, it was possible to make some sol gel. You don't need a lot, because this vinyl compound is very poorly reactive. So let's say if we put 8% in the feed, we obtain 2% or 3% in the polymer, which is enough in order to enable the cross-linking. So it's a kind of sol gel cross-linking that we achieve. Okay, I understand that you can say, okay, we put silica inside, and in acidic conditions, obviously, the membrane will not be very efficient. We didn't try that. We didn't try infused cell test and even the degradation. But what was very interesting on this membrane, that the conductivity was 43 millisiemens per centimeter at 65 Celsius, and we could reach 12 millisiemens per centimeter at 120 with 100% relative humidity, which is quite interesting for this work. So again, the design of a depolymerization which was non-controlled. The second approach I would like to talk about concerns the chemical modification. And there are a lot of strategies which have been developed everywhere in the world on, let's say, the chemical modification of polyparaphenylene. This was a group of Régis Mercier again and Céline Lenivin. They use substitution, nucleophile substitution of phenol containing sulfonic fluoride compound or sulfonate adjacent to CF2 in order to make some chemical modification of this paraphenylene to have this side group containing aromatic and then sulfonic acid adjacent to CF2. So the conductivity was not so high, but the target was for direct methanol fuel cell, in which they have successful results. Another strategy which is very well developed in the world by Suldom in Finland or Scherer in Switzerland, Nassef in Malaysia, Liang in China, Slade in UK, or even in Japan, I know a lot of groups are working, is to take a fluorinated polymer and to make some irradiation. So you can do irradiation by ozone, by electron beam, by gamma ray also, and indeed it's not very well specified if you have trapped radicals, if you make a simultaneous irradiation in grafting, adding a monomer, or if you make hydroperoxide or peroxide. But this kind of systems are very efficient because these macroradicals enable to initiate the polymerization of M monomer, or this peroxide or hydroperoxide also can initiate the polymerization. So in this case, you have a fluorinated backbone in which you have graft made of a monomer. And if you case styrene, which is very easily polymerizable under radical condition, so under macroradical or macroperoxide, you can have a graft copolymer, let's say with PVDF or PTFE graft polystyrene, that you can functionalize by acidification in H2SO4, for instance, in order to make some graft polysulfonic acid styrene, polystyrene. And for instance, Suldom in Finland achieved some conductivity up to 100 millisiemens per centimeter. However, the problem is durability, because this styrene compound can undergo some beta elimination and not very appropriate in long-term fuel cell test. So the approach we had was to try to find out again some depolymerization with VDF, vanillin fluoride, hexafluoropropylene, and this monomer. I say this is the cousin of acrylic acid. But acrylic acid polymerizes very easily. But if you put a CF3 in alpha position, it does not homopolymerize. This is a unique sample given by Tozo Company. Tozo Company is in Tokuyama, and they supply us this sample. So I'm very thankful for this company which enabled to get this sample. And we had, interestingly, it's a very good comonomer for VDF, so you can do a PVDF with carboxylic acid, which is very interesting because carboxylic acid can be modified and even you can attach some nanofillers inside. So the idea was to make tail polymerization and under conventional polymerization or in the presence of the chain transfer agent in order to make some controlled radical polymerization. I will speak about that in another seminar. And the different chain transfer agent can be either iodo compound or diodo compound. Initiator can be different peroxide or persulfate. We can work in water or in solvent. And what was very interesting, by NMR, I don't show you NMR today, but we have a random distribution of alternating structure between VDF and this MAF, this alpha trifluoromethyl acrylic acid, separated, so it's a block of this alternating copolymer separated by one HFP because hexafluoropropylene does not homopolymerize. So I found that this structure very, very interesting. And we say, okay, this can be an interesting approach. Molecular weight were ranging between 25,000 to 75,000. The TG increase when you increase here the content of MAF, which is very interesting, but when you increase the content of MAF, the thermostability is decreasing. And indeed, we see that we have a lot of decarboxylation. Let's say here we have 1% of MAF, 3%, 35%, 37%, and 40%. So this means the higher MAF you put, the higher decarboxylation you have in your system, and you have a very poor thermostability. So this is a TG you heat under air. So the idea was, okay, to put carboxylic acid is not very good for conductivity. Can we modify this carboxylic acid in order to have sulfonic acid, for instance? And this is exactly what we did. Started from this tail polymer, we decided to make a reduction of carboxylic acid in order to make a primary alcohol. And this is very interesting because in this case, by proton NMR, it was possible to confirm the content of MAF in the system. Okay? Because in proton NMR, we have, of course, some overlapping of the two protons here arising from MAF and VDF. And then these primary alcohol are very reactive with phenol under mid-soluble reactions. Okay? And if you react with phenol sulfonic acid, you can graft on your primary alcohol some aryl sulfonic acid. And this was a strategy we use. So just understand, from gas, because these are gas, we obtain a material and we obtain a membrane. So recently it was patented by Atomic Energy and CNRS, and finally we got the authorization to publish, and we recently published this paper. So this enables to have some conductivity. The conductivity is not so high because at this stage it was necessary to blend with a commercially available PVDF compound in order to have well-standing mechanical properties. But we are still working on that, even making block copolymers. Unfortunately, I cannot speak about that. And it seems that a better approach and higher conductivity are reached in this system. I would like to talk about another interesting strategy developed by Surya Prakash in Los Angeles. This is the group of Ola. Ola got the Nobel Prize in early 90s, and they work on superacid. And this group decided to blend or to embed some styrene into PVDF, okay, to put styrene and also divinine benzene, and then from the mixture to make a polymerization, okay, and sulfonation by chlorosulfonic acid in order to have what is called a semi-interpenetrate polymer network. This was very interesting because the polarization curve seems to be better than that of Nafion. Nafion is C, and these are the different polymers they obtain, okay? And the power generated in the system was higher than that of Nafion. So they can reach about 50 milliwatt, okay, in order to have, compared to Nafion, in this condition with 55% and 100% humidity. So we try to be inspired by this work, and this is very interesting to read literature. So I encourage the young PhD students to read. This is very important to read literature. And we say it should be interesting to make, to design also an IPN with a fluorinated group polymer, and another polymer which brings the sulfonic acid group. And this is exactly what we try to design. In a network, we try to do a network with some colleagues in Lyon, okay, with a polymeric counterpart coming from diacrylate, and here to have IPN, so an interplanetary polymer network, because in this case we need high conductivity brought by sulfonic hydrocarbon polymer, and also we need low hydrogen permeability, good dimensional stability, good mechanical property, good chemical stability brought by the fluorinated counterpart. And this was another project, a French project, so you are going to say I'm very patriotic with French, but this project was also involved with some colleagues in atomic energy here, in Lyon, Régis Mercier and Eliane Espluche. We also participate with some people in a laboratory of polymers in Cergy-Pontoise near Paris, and all of them had a specific task. So this means that we were able to supply some fluorinated monomers. Another group was able to prepare some precursor containing conducting polymers in Lyon. Another group was able to make some scale-up, a small size company also, and in this way we had also the help of Spram, Gérard Jebel, who is able to calculate by Sachs what about the morphology and if there is some peak assigned to the conductivity, and also the water sorption, the gas transportation, and then the fuel cell test. So this was for us a very challenging program, but in 3 years I think we were successful, and I try to give you some summary of that. So this is the sulfonated peak, which was tried with an ionic exchange capacity of 1.6 millimoles per gram, equivalent weight 600, and this is the diacrylate optyl fluoro compound that we prepare in a good way, and to mix them together in one pot, to exchange the sulfonic acid, the sulfonate into sulfonic acid, and then of course to change the composition in order to have a good compromise between the conductivity and the mechanical, thermal and oxidative stability. So what we did was, of course, after making the IPN, or the semi-IPN, sorry, we did some cryotherm, and you can see that we have a small phase separation at the microscale. This light is assigned to the fluorinated material, while here all the dark spots are assigned to the sulfonic peak. And in this kind, you can see that there is kind of percolation in order to allow the conductivity from the sulfonic acid groups. Okay, and this was also unexpected to see that. The thermal stability was also carried out. Whatever choosing the sulfonated peak, you have a loss at about 100 because you have water escape and desulfonation. And this is the sample that we have from the fluorinated diacrylate. And you can see that the thermal stability of the different samples containing different amount of sulfonated peak and the fluorinated polymer are intermediate between the thermal stability of the fluorinated polymer and the fluorinated and the sulfonated peak. Storage modulus, mechanical properties also were intermediate. This is the that of the sulfonic peak, and also this is from the oligomers made from polymerization of diacrylate. And you can see that we have also with 60-40, 50-50 and 40-60, we have really intermediate, showing that we have a kind of stable system. It was necessary also to investigate the reactive conductivity at different content of peak, because this polymer brings, of course, the conductivity. You can see that at low component we have a low conductivity, and then we can reach even higher than that of Nafion when we put almost 90%. But 90% in this case, you see that we lose in durability, okay, and we have a lot of swelling, because you have to see that the membrane is generating a lot of water, and of course your system has to be very stable in water. So indeed, working in this condition at about 60% was the best compromise, because we don't have much swelling, and also we have a poor, let's say, a less drastic degradation of this system, though the conductivity was acceptable, about, let's say, 80 millisiemens per centimeter. So we decided to do some polarization curve. When you do that, you voltage versus current density. This is Nafion 112, showing a very good polarization curve, showing that really this is the reference in the field of perfluorosulfonic acid group. Nafion is very good. I think Flemion also is very good also. And when we have this kind of mixture with 60% of sulfonic peak and 40% of diacrylate, we achieve reasonable polarization curve at 600 current density. We are about 0.5 voltage, which is not so bad. You know that this kind of conductivity can be assessed by electrochemical impedance spectroscopy. You plot the imaginary system versus the real system, and so you have this semicircle which is related to the resistance of the membrane, and by an equation, by the reverse of the resistance of the membrane, the thickness and the length, you can have the conductivity, which is very interesting. So before finishing, I have a couple of examples also. This is a group, Kim in Korea, who did a lot of ATRP grafting onto copolymers made of VDF and chlorotrifluoroethylene. Amazingly, I was very surprised because they can cleave CCl bond in order to insert some sulfonic polystyrene, and from that, the chlorine here can be modified in an azido compound, and this azido is able to undergo a photopolymerization in order to have a crossing network. And this, I found this very interesting, this approach very interesting, because they show that the cross-linking increase the tensic strength, increase the mechanical properties, reduce the water uptake from 300%. So this swell 300%, okay, so it can not be used under few cell condition, but after cross-linking, they reach 83%. It's still high, but you can see a drastic loss. And the conductivity here was slightly reduced, but they could achieve 68 millisiemens per centimeter. I found this approach of cross-linking very interesting, because if you can cross-link polymers, you can have really better enhanced mechanical thermal oxidative properties. Okay, and thanks to my co-worker Aurélien Soules, who did his PhD 2 years ago, we did some iodine transfer polymerization of styrene in the presence of diiodo compound. Okay, so it was possible to have a polystyrene which was telecalic, in which the N group were iodine, and this iodine could be modified into azido compound. So we have a nice azido conversion. After, let's say, 2 or 3 hours, we have almost quantitative conversion of the azido group. This shows that we have a linear dependence between the degree of polymerization of styrene versus the conversion of styrene, showing that we have controlled radical polymerization, and also the polyspermicity index is lower. Let's say in ITP, iodine transfer polymerization, you cannot get 1.1 as PDI. You go usually to 1.4. But this was very interesting to combine this control radical polymerization and also the cross-linking. Indeed, we also prepared this kind of diazido compound containing fluorine, and we mix them together with the styrene, okay, after making sulfonation and then click chemistry by photopolymerization of the azido. So this gave a crossing system which was very interesting to investigate. And as you can see here, the conductivity versus the temperature, so you have a temperature here, shows that we have very interesting sulfonated membrane here, you know, at 80 or even higher, and even better than that of Nafion membrane. So for us, this is Nafion, and these are the different systems that we obtain for the conductivity of a cross-linked membrane. So the cross-linking also in this system enables to have something very special, which has to be understood here. But Nafion, I told you, it's a reference. If I have 5 minutes, Nafion is a very interesting reference membrane, but they have 4 limitations. One limitation is methanol crossover, so you cannot make any methanol direct fuel cell. The cost, still expensive, So I apologize for the currency. We speak in euro in Europe. So maybe it's 50,000 yen, about 60,000 yen per meter. It's intolerant to carbon monoxide in impure hydrogen, and it dries from 80 Celsius. So this means that if you want to achieve a good conductivity at temperature higher than 80 Celsius, you can have some problem and you have a loss of performances from 80 Celsius. On the other hand, polybenzimidazole are very interesting from high temperature, from 140, 160. So there is a window between 80 Celsius and 130 in which we have to find out new materials. And what we try to find out with our colleagues at the University of Montpellier, Jacques Rosière and Deborah Jones, who are very experts in fuel cell, we try to find out water by what is called amphoteric solvent, in which you don't have a Bluetooth mechanism. You know, usually you have a proton hopping. The proton is mixing water, making hydronium ion, and then you have some mobility by the water. Here, the system, you don't use water. So how come the conductivity is possible? This is by diffusion mechanism. So you have a hopping with either phosphonic acid or nitrogenate heterocycle. You have a hopping system from, let's say, benzimidazole group. This is a donor, and this is an acceptor side. So the proton is changing, is moving, shifting from one side to one another. And in this case, you can have a proton diffusion. And for this, we try to fulfill a strategy starting from acceptor-donor copolymerization. Chlorotrifluoroethylene is an acceptor monomer because of a high content of fluorine onto the carbon atom, and the vinyl ethers are donors. So we could do some alternating copolymers in which we have 50% of CTFE units and 50% of the vinyl ether containing chlorine. And this chlorine can be chemically exchanged by arbuzole reaction with phosphonic acid or with imidazole or benzimidazole. And this is exactly what we did. Also, we did some chemical modification in order to have a monomer, a vinyl ether containing an imidazole protected, otherwise you have some Maillard addition. So this copolymerization enables us to have some alternating copolymers and then hydrogenation in order to deprotect and to have this blended membrane. The conductivity was not quite excellent. When we mix them with sulfonated peak, you can see that the higher the content of a copolymer, the better the conductivity, but we want to work at low relative humidity, at 30%, in collaboration with Peugeot company, the car company in France, and really it's a difficult challenge to reach high conductivity on that. So this was done at 100 Celsius. So we decided to change and to have a copolymer on which we make chemical modification here. So with this kind of protected imidazole or benzimidazole, we are still working on that. There is one PhD still working on this system. And this is the evolution of conductivity versus the ratio of imidazole and sulfonic acid coming from the copolymer and from the sulfonated peak. And you can see that the best conductivity can be achieved when you have a ratio of 1:1. So this means that you need, at low temperature, you need sulfonic acid. We start to generate some current, and then at higher temperature, the copolymer containing imidazole or benzimidazole is taking the way to maintain and to release some current. So these are the thermal analysis. I don't insist on that. What is interesting here, this is the water uptake. So when you have sulfonated peak, you have very high water uptake, especially at 100 Celsius. And when you reduce this content, you are going to lower. This is very important because we don't want a big swelling in the system. So the other approach was done by another PhD student, by Russell Tayou, coming from Cameroon. He was one of my best students, very hard worker. And he decided to make some chemical modification of the chloro compound by the phosphonic acid here. So this is the copolymer. It was diluted in DMSO, and then casting evaporation DMSO with a special cycle in order to be very careful in the evaporation of this solvent. DMSO boils at high temperature, so we have to work in the vacuum, etc. But this was a nice system. Even we put some, when you have only this alternating copolymer, the ionic exchange capacity is 7. wow, this is very high, 7, but it swells a lot. It swells a lot. Phosphoric acid is like a sponge, taking water a lot. So it was necessary to put some hydrophobic group here in order to reduce. Of course, you reduce ionic exchange capacity, but also you reduce the water uptake. And in this case, at 90 Celsius, you can see that we have this kind of conductivity versus the relative humidity. So we try to be here at 30 Celsius. This is the requirement for car to work 7,000 hours at 100 Celsius, 120 Celsius with 30% relative humidity. This is the requirement for cars. And indeed, what we can see at 120 Celsius, we had, let's say, still poor conductivity, but interesting, let's say, encouraging conductivity to do some further work. So we're still continuing working on phosphorus, working also on imidazole. So before finishing, I would like to give you some pictures about the history of the fuel cell. Already, General Motors supply an electrovan with an autonomy of 200 kilometers in the late 60s. It was very interesting because the fuel cell was 5 kilowatt, and you see Austin car in the 70s. You have this on the roof. This is the reserve of hydrogen, but it didn't drive very far, a lot of time. Nowadays, really, Japan is a leader in the world competition, and I'm very glad today to give this talk because I'm sure that you will find a lot of ideas. Honda and Toyota are making a lot of things, and Honda has already comes from times to times the Honda cars to fuel here in Kyushu. So this is for me very impressive, kind of dream becoming a reality. So the autonomy is 600, more than 600 kilometers. The tank pressure 35 megapascal. This is what you have. Or the tank pressure 70 for an autonomy of 800. So in conclusion, what I would like to focus on is the road is still long. A lot of work is done in the different components of a fuel cell, whatever the membrane, the catalyst, the MEA, the fuels. But I'm sure that here in Japan, in this nice center, you will face these difficulties, and you will overcome and find very nice project in order to find out new membranes, a new catalyst, and suitable MEAs, and to find maybe a new fuel. I know that you have a hydrogen production here, but why not to use ethanol, methanol, ethylene glycol, bore hydride for alkaline fuel cell. Unfortunately, I don't have time to speak about alkaline fuel cell. I have 2 people in my group working on that, and also to reduce the number of the MEA. So before finishing, I would like to acknowledge all the people involved. So of course, a lot of workers in the lab. We started this work 10 years ago in collaboration with Hydro-Quebec in Canada. And then we had a couple of student postdoc working, my friend George Kostov in Bulgaria, Frédéric Baucher, also Laurent Sauguet, PhD, all of them have been PhD, all of them. And this was for me very challenging and very interesting to discover a new world of fuel cell. And also I want to thank all the partners in French projects and also Tozo. And also I want to thank you very much for your kind attention. Okay.